Chatelier's principle. When a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. So this is something you should have heard of in a previous chemistry class. We've got a population analogy here. We've got some people in Narnia and some people in Middle Earth. If the population in Middle Earth grows, there's some sort of a population explosion, maybe there was a big blizzard or a power outage, maybe there was, an alien spaceship came in and dumped off a lot of halflings or something. Anyway, you get a lot more people here. That's going to affect the rate at which people are moving back and forth between the countries, right? This equilibrium is going to shift because the equilibrium is dependent on the rates of the forward and the reverse reactions. The rate of the forward reaction depends on the concentration of the reactants. Do we care how it depends? In chapter 15, no, we don't. In chapter 14, we did. Is it first order? Is it second order? We don't care now. But it depends on the concentration. The reverse reaction depends on the concentration of the products. So if we increase the concentration of the products, that increases the reverse reaction. That has the effect of reducing the increase that happened here. I kind of like Le Chatelier's principle because I'm not a big fan of change unless it's my idea. And so whenever something changes, I resist it. So I push back. No, let's just make things as much the same as we can. And so here, the population in Middle Earth suddenly grows. It's like Le Chatelier's principle says, equilibrium is going to go, what can we do to undo what they did to us? Well, we can shift some of that over here. And so that's Le Chatelier's principle. A system at equilibrium tends to maintain that equilibrium. It bounces back when disturbed. So we can add stuff over here, but it will shift, and the end result is that the equilibrium expression and the equilibrium constant are still valid. So, effect of a concentration change. Looking at this reaction between N2O4 and NO2. If we add more product, that's going to increase the reverse reaction rate, right? So we say the equilibrium will shift to the left. It will cause the N2O4 concentration to increase. It will cause the NO2 concentration to go back towards what it was originally. We can look at this in terms of Q as well. Before we added NO2, Q is equal to K. Remember, Q is calculated the same way, but Q is calculated at whatever conditions you're at, and K is at equilibrium. Immediately after adding that NO2, so we can write the expression here. So Q is equal to the NO2 concentration squared divided by the N2O4 concentration. So immediately after adding NO2, this term on the top is larger. We're saying immediately, it hasn't had a chance to do anything, this one's the same. So obviously Q is going to be larger. When Q is larger than K, the reaction goes to the reverse direction to reestablish equilibrium. Here we have it in pictures. So, adding more NO2. Now there's more NO2 molecules that can react and form the N2O4. And so that will occur, the system will shift to the left, we'll get more N2O4 forming. If we add reactant, the equilibrium shifts to the right. I'm putting more in here that increases the rate of the forward reaction. It is causing Q to be smaller because now Q equals, again, the NO2 squared over the N2O4. Immediately after adding N2O4, the denominator is larger. That makes Q smaller. When Q is less than K, the reaction goes in the forward direction until Q becomes K. Okay? Here's a graphical representation of this. It's like giving you multiple ways, because people's brains work in different ways, right? So hopefully one of these things, you're like, oh, okay, that makes sense. So here we have concentration of N2O4, concentration of NO2. We're at equilibrium, and then we're going to disturb the equilibrium. So we're adding a bunch of NO2, and so this concentration goes up, and then what happens is this will begin to go down, and this one, pointer stuck, this one will go up a little bit, right? They're not going to go, the shapes of those curves are not going to be exactly the same, because this has got a coefficient of 2 and that's got a coefficient of 1. But an equilibrium will be reestablished. Both of these concentrations are higher than they were originally. But when we talk about the equilibrium shifting, we're saying from this point where something was done, which way does the reaction proceed? And the reaction here is going to proceed so that we reduce the NO2 and form more of the N2O4. So that's going in the reverse direction. Here we're adding the reactant, again, starting at equilibrium, and we get this big spike in N2O4 because a bunch of it was added. That's going to cause the forward reaction to occur. So this will react to decrease from what it was changed to. It's trying to go back to this. It's never going to get back there completely, but it's just going to try. And then this one will go up a little bit. Does that make any sense? Oh, just one point. On the worksheet, there is a question that says to draw a diagram showing how the concentrations change. This is the kind of diagram it's asking for. So summary, you increase the concentration of reactants, the reactant shifts to the right towards the products. You increase the concentration of products, it causes it to shift to the left towards the reactants. What if you decrease the concentration? If you decrease the concentration of the reactants, the equilibrium, the reaction says we need to replace that. And so the reaction will shift to the left towards the reactants to replace them. If you reduce the amount of products, it will shift towards the products, trying to bring it back to what it was. So consider the following reaction in equilibrium. What is the effect of adding additional Br2 to the reaction mixture? So we're going to add Br2. It'll shift left. What's the effect of adding additional BRNO? It'll shift to the right. If I add some of this, reaction says, I don't like that. I'm going to shift over here to get rid of some of that. Adding Br2, I don't like that. Why can't we just leave things alone? We shift over that way. So what if we're changing the volume or the pressure? So for gases, pressure and volume are related. They're inversely related. You increase the pressure, you decrease the volume. So if the volume of the reaction mixture changes, that causes the pressure to change, and the equilibrium will shift to minimize the change. So what we're going to do to make this a little simpler is we're going to assume that these changes occur at constant temperature. Because if you let the temperature change, then things get really messy. So here we have a reaction in a cylinder with a movable piston. We've got nitrogen and hydrogen reacting to form ammonia. It's in equilibrium, everything's nice and balanced and everything. What happens if we push down on the piston? What does that do to the volume of the reaction mixture? It decreases. So the volume decreases. What does that do to the pressure? It increases. So we've increased the pressure. The equilibrium then wants to decrease the pressure. How could pressure be lowered? We can't change the temperature. We can't change the volume. What's the other thing in the ideal gas law? Moles of gas. We could change the moles of gas. We can lower the pressure by reducing the number of moles of gas. So reduce moles of gas. So remember, with gases, it doesn't matter what the particles are. It's just how many there are. So on the reactant side, how many moles of gases are there? In the equation, 4. We've got 4 moles of gas. We've got 1 nitrogen and 3 hydrogens. And in the product side, how many moles of gas? 2 moles of gas. So by shifting the equilibrium, can we reduce the pressure? If the reaction goes forward, we have fewer moles of gas, and that's going to cause the pressure to go down. If we go in the reverse direction, we're going to create more gas molecules, and that will increase the pressure. That make sense?
Yeah.
So we put pressure on this, and it says, I don't like that. You've made me change, right? You identify way too much with this. How can we reduce the pressure? By shifting to the side with fewer moles of gas. So this will cause the reaction to shift to the right. Everybody with me on that? What if we add some helium gas?
It's going to make more reactants.
Well, what's your reasoning on that?
Helium. If we add helium gas by itself, it's going to add more molecules to the left side, which is the reactants.
Well, we've got a mixture, right? We've got a mixture, and because the weird thing here is helium isn't one of the reactants or products, right? Were you looking at H and helium?
Oh, yeah.
That's okay. That's okay. Easy mistake, right? So helium isn't one of the reactants. And we're like, well, what do we do here? Well, does adding helium to this container change the pressure? Yeah, it does. Adding helium increases the pressure. How can the pressure be lowered? By going to the, shifting to the side with fewer moles of gas. So it'll shift to the right. So adding helium increases the pressure. So that will have the same effect as pushing on the piston, squeezing it together. So it'll shift right. I did write those words. It's going to crash here in a minute. No? Okay, so adding helium increases the pressure, will cause the reaction to shift to the right again. Here we've got an illustration of that. Here's our reaction mixture. We press down on the piston. That causes the volume of the container to be smaller, causes the pressure to be increased. On the left, we have 4 moles of gas. On the right, we have 2. It's a little bit like carpooling. So over here, we have 4 cars going, and here we have 2 cars going. And if things are very congested, then people are more likely to carpool, right? If there's no problem with traffic, then people are like, oh, I'd rather bring my own car. So by shifting to the right, we can make things more compact. There's fewer particles, fewer vehicles. There's still the same number of atoms, there's still the same number of people, but now they're packed into 2 cars instead of in 4 cars. Over here then, if we lift up on this and increase the volume of the container, that decreases the pressure. Equilibrium doesn't like that either. What can we do to make that up? It'll shift in the other direction to replace the pressure. Now, it shifts in that direction. It never gets back to exactly the same concentrations or pressures, but it's going in that direction. Any questions?